So, what is MTU? Who is MTU? What we are dealing with? With that slide, I would like to start. We make aviation engines. That is our business, and we have three columns of our business. The first of it is the commercial OEM business. That means we sell engine, we sell parts. The second column is the military OEM business. It's a smaller portion of our business. And the main column is the commercial MRO. Here we have two-thirds of our business, and that is where we are working in. Yeah, we have last year 6.3 billion of turnover and an EBIT of 800 million. Yeah. With additive manufacturing, we are dealing since 1997. We made some first rig tests in 2007. When we introduced additive manufacturing in our manufacturing process chain, we are producing rotating wheels. These wheels are rotating with 6,000 revolutions per minute, really faster. And with highly loaded parts we use since 15 years, and they really give us a high productivity in grinding. Yeah, the first commercial part that we really get certified were in 2013. Two smaller parts, the borescope eyes we call them, uncritical parts but highly loaded parts. And since this year we are proud to say we have introduced the first full bionic parts and have them certified, 3 of them, with a weight reduction of 50%. 50% weight reduction that will help us in future to build larger and more efficient engines. Yeah, to come to this way, we had to develop a lot of technologies from design to additive, process simulation. We have very good tools. We can simulate the material properties. We can simulate the distortion. We improved the machines together with our partner EOS. We improved the process. We have our own online monitoring system that tells us exactly which layer is good, which layer is out of the tolerance. We see systematic and local deviations, which give us a very good overview about the process. Material is characterized for Inconel 718. Powder recycling is in the meantime certified at MTU, so we use all the powder completely. Surface finish, very important point. Here Justin helped us a lot of. Thank you very much. Non-destructive inspection was also a very important step. We have very flat defects at MTU, at additive manufacturing due to the layer-wise building. These very flat defects are very difficult to find, but we have found also here a way. We have a very good quality concept, and our certification strategy is discussed with the authorities, with the FAA, with EASA, and we have here a very good process. Yeah, we have today 8 machines, all from EOS. The latest one is our M300, a multi-laser machine. We are also very proud to have this machine. It has a much more better material quality than the older machines due to improved shielding gas flow that helps us a lot. And fully qualified is Inconel 718, and with titanium we started to qualify, and we other materials we can produce for third-party business, but we are not qualifying these materials on our roadmap. Yeah, the first serial application you see here, this borescope eye, it's highly stressed. We have produced so far more than 8,000 parts. We have only very good field experience with these parts. The parts are doing what they shall. And what did we learn from this first parts? This was a full substitution of a milled part. We learned it's very hard to achieve the target costs by pure substitution. We also learned that we have very high cost for post-certification. That means an engine is running, the engine is certified, the part is certified, and now to come with a new process and certify this in aviation again takes a lot of effort and is very costly. Yeah, and also we learned the machines are not where we want them. The availability is still too low. Here is some way to go. And what we also learned, the post-processes are also very important to get cost-effective parts out of this process. Yeah, here our brackets, full bionic designed. Serial production is started, 50% weight reduction. That is where we want to go. We will not find at every part 50%, but we will find everywhere a weight reduction. Also for the next part that is going to be certified, it's a bearing housing, a really highly loaded part, axial loads and radial loads. And this part we also will have around about 10 to 20% weight reduction, even though it's an approach of substitution. Why do we save so much weight? We have a better material than casting, and we have lower tolerances. Yeah? That helps us to save the weight. Yeah, why do we in the aviation, in the engine business, additive manufacturing, what we think we can win with it? First of all, functional improvements, yeah, saving weight, getting more efficiency for cooling air, getting bionic designs, taking out the material that is not needed from structure's point of view. Later on, we will print obsolescence parts that you cannot get anywhere else because your supplier does not exist anymore. It's a contribution to vertical integration, not to outsource so many things. Currently, we have the trend to insource a little bit more than we did in the former times. Yeah? Everybody knows the problems with the supply chains we have today. Here, additive will help us. In the future, it will help us to reduce our inventory. Instead of many parts, we have only a few portions of powder on our stock. For toolings, we use it, and also in the future time for MRO repairs. Yeah, what are the challenges? Yeah? The most challenge that I today see is the cost. Yeah? We don't introduce parts simply to the reason that it's additive and it's new and it's funny, and that we don't do. It must save cost and we must earn money with it. And here we have a problem. Today our complexest casting that we have at MTU in comparison with additive manufacturing, we are today from the manufacturing cost on the same level. Yeah? So that means we have no cost advantage and we have no positive business cases to introduce parts where we have high one-time cost. Yeah, the reasons are mainly quality assurance, ultrasonic testing, computer tomography. That is something where we work on, have to work on. We have good ideas what we can do there. It's also machining, of course, and surface treatment. Here we come, and with our partners together, we also will work on the surface treatment, and with all the next technology steps and next improvements of the costs, I would assume in 2-3 years we are much better in the cost situation in comparison to castings than today. Yeah, leading over to surface treatment, it's very important. Why it's important, you see here this picture of a typical additive manufactured surface. You see here baked particles where we have the risk that they can lose during using the engine, during service, that by shaking and by vibrations with particles could shed. That must not happen. It would be a risk to the engine. So for this reason, we have to do surface finishing for 100% of our parts, internally and externally. Yeah. And Inconel 718 is not a very nice material. It's a very tough material. And for this reason, it was already very complex to find a process that really can help us here to improve these surfaces. We have a requirement that we need a high geometry flexibility. That means we would like to have the same material removal inside, outside, not rounding the edges, not attacking the surface. We have to get rid of these loose particles, and we have to improve the fatigue life. Everybody can imagine that this poor surface will not have a very good life, and for structure mechanics you have high stresses here in the peaks, and also here we need something to improve. And the last point here, FPI, stands for Fluorescent Penetrant Inspection. That is a typical quality assurance process in the aviation industry. That means we bring on this fluorescence afterwards on the part when we wipe it away, and afterwards we see where are cracks, because in the cracks we still have this penetration fluid, but as a precondition that we can use this process, we have some requirements on the surface. We shouldn't have background fluorescence that you see here on this left picture. So that is something you cannot evaluate because you have penetration in the normal surface and not in the cracks. And on the right side, you see a surface that you can very well evaluate. Yeah, and all these requirements are fulfilled by the chemical polishing process from our partner RAM Surface. And from this point, I would like to give over to Justin and to make the second part of the presentation and tell us how great is your chemical etching process.
Thank you very much, Dr. Kraus. So we'll talk a little bit about the technology that we utilize. We'll focus on the chemical polishing. That's what's being utilized here with MTU. We have another process that we utilize sometimes as a secondary operation. We won't speak about that here today, but if you're interested to learn more, we have a booth downstairs. We'd love to have more conversations with you. So speaking about the chemical polishing process, as it might sound, it's a chemical dissolution process, right? It's a controlled one. We've developed all of our own formulations to optimize the alteration of the surface texture. We want it to be as controllable as possible. And we like it because it's a very flexible process. It can deal with many complex geometries, like Dr. Kraus's components. It's effective on narrow channels, lattices. It's useful for removing support structures. So it can be used in a lot of different ways. It has some benefits. So as I mentioned, it's highly uniform in its material removal. It's helpful for fatigue life. You heard Dr. Kraus reference that. That's one of the first areas in additive where we really found success, was fatigue critical components. It's also useful for cleanliness, flow properties, things along those lines. So it's all good things, right? Well, not quite. There's process challenges as well. So it's a chemical process. Therefore, it's generally alloy specific. So if you come to us with a new alloy that we've not worked with before, or we have limited experience with, there can be some time to optimize and develop that, and that can mean money as well. It also is commonly affected by heat treatment. So there's been occasions where we've done a very nice sample part for someone, and then the real part comes and it reacts very differently. It's because they didn't heat treat the sample components, right? It's sensitive to all these things. It's the chemical interaction with the surface, so we need to understand all of these different phenomenon. So not necessarily the easiest process to implement. It has to be for the right components and the right applications. What we're showing here is actually some problems where we were doing a project with the US Air Force, and we had some components that came with a very thick HIP oxide layer. And in the chemical polishing process, we were having a regular breakthrough of that oxide layer and actually roughening the component. So the opposite of what we want to achieve. So in this case, we had to develop a pre-process step to remove that HIP oxide layer so we could then get a uniform reduction in the roughness in the actual component. So again, it just comes back to there's some steps that are required to implement our process and to utilize it. You can't simply snap your fingers and necessarily have it be perfect. So cost. Cost is a big thing. We're a very good technical solution, right? But as we're trying to go into production, we need to be able to also control costs. In a development project, a lot of your costs are going to be driven by labor, right? But as we go to production, labor becomes less of a challenge, and now it becomes much the process consumables. Again, we're a liquid chemical-based process. Most of these chemicals are, in general, single use. So we have to learn to understand those elements and really drive to optimize those things as we want to be able to be implemented and support programs like MTUs. So obviously you see labor, direct, indirect costs. What does all that really mean? Well, if we're going to be able to be viable from a production perspective, we need to really understand the details of the chemical process itself, understand the heat of the reaction, right? One of the key critical quality elements for us is controlling the temperature because it controls material removal rate. That is easier said than done, right? If we're going to try and get our volumes down so we can really have high levels of cost efficiency, so we can reduce the required materials for the neutralization of the process when it's done, and the waste treatment, we really need to be able to control that reaction itself. And that means both understanding what's going to happen at various temperature levels, understanding the material removal rates, and ultimately being able to control those at a very high degree. So that's kind of where we are right now in the process. So building from these engineering solutions to actually going to full production applications, that's the journey that we're on right now, that we're trying to work with MTU to that end. So if I can close with a few other thoughts here is, with post-processing, if anyone tells you they have the solution for all of your problems, you should walk away. It's not the right answer, right? We're all tools in a toolbox. We're the right tool for some things, not for all things. Some of the things to look at us for is complicated applications, right? If there's a simpler process that can get you the surface requirements that you need, you should probably use it, because it's probably going to be cheaper than I am, right? But for the right components, where there are non-accessible surfaces, or where there's an opportunity to possibly combine operation steps. Perhaps we can do your support structure removal for you while executing the surface finishing. Perhaps we can do other cleanliness improvements as well, as reducing the roughness. These are all good use cases for a process like ours. Other things to just, in a more general sense, is that if you are producing a fatigue critical component, before you worry about surface finishing, make sure you have good component density. We've done a lot of different studies with a lot of different people. And yes, you improve the surface finish, you'll improve your fatigue life, but it'll be limited by the next weakest link in the chain. And if you have subsurface porosity, things along those lines, the benefit will not be maximized. And as we're talking about an additional processing step, we're adding costs, we need to maximize the benefits that we're generating. We also need to ensure, might seem obvious, might not, there's adequate material offsets for a process. We're a subtractive process, right? We're taking material away. If you come to us with a part that is already at final dimensional tolerances, we probably can't help you. And then last but not least, look to avoid unnecessary or redundant post-processing steps. So a big thing that we've been working on recently is this development of the capability to remove support structures with our chemical polishing process. Utilize that, right? If we're going to use our process to improve your surface, let's also take your supports off so we can take away other operation steps and help to reduce some of those costs that are being added to your components. Thank you very much.